let him get it and then it's fine. Okay. So all right. So yesterday we started really looking at uh, um, delta R, delta rho. Okay, delta rho essentially looks at custodial symmetry. Any relation which preserves this essentially. Okay, it is what it requires. If this ratio is correct. So why this ratio is important? Because this gives you the W and Z masses, the neutral component of the thing, and the charge component of SU2 gauge bosons when they are broken. So they are very crucial. Essentially, it tells you what about the custodial symmetry breaking. It's very crucial to custodial symmetry breaking. And then we looked at delta R, which is corrections to GF by you want the Fermi coupling constant essentially. So we also looked at how these corrections come into it. These are related. Okay, delta R contains more pieces compared to delta rho. Okay, this is also very strongly constrained. Essentially, delta rho is so close to 10 power minus 4%. ಚಾರ್ಜರ್ ಬಂದಿದೆ ದೊಡ್ಡ ಕೇಬಲ್ ಒಂದೊಂದು ಚಾಕ್ಸ್ ಇದು ಚಾಕ್ಸ್ ಬೇಕು ಹಾಂ ಅಲ್ಲಿ ಕನೆಕ್ಟ್ ಈ ಕನೆಕ್ಟ್ ಇಟ್ಟು ಚಾಕ್ಸ್ ಬೇಕು ಈ ಥರ the other ones don't write properly white color ಈ ಥರ ಇದು ಸಾಫ್ಟ್ ಇದೆ ಇದು ಇದಿಲ್ಲ okay, so this one contains many pieces. So delta R is again delta rho plus so and so and various pieces, vertex and box pieces. So it contains many things, and this is also strongly constrained coming from muon lifetime. So this is 1.00004 or something. Okay, plus minus some error bar which is in this decimal place. Okay, whereas muon lifetime is also very strongly constrained. Essentially, yesterday I gave the numbers or thing like that. So just muon lifetime itself is very strongly constraining. Now this is a direct measurement. Muon lifetime is actually a direct measurement, whereas delta rho is inferred from experiments. Essentially, it's inferred. You cannot directly measure delta rho. So what you can measure directly at experiments, essentially sine square theta W. Okay, you can measure sine square theta W, and this is related to the observables at left. So we looked at two observables essentially at cells D with polarized electron beams, essentially polarized targets. This was at slack. Okay, this was at slack. They had a much lesser what do you call sensitivity compared to LEP, because they don't produce millions of Z's like LEP produces. Okay, at the Z pole they produce about 10,000 or something, 20,000 in the lifetime. Okay, the other one is, we saw the formulas for this, essentially forward backward asymmetry, sine theta 0 to pi by 2 minus sine theta pi by 2 to pi. Okay, of at LEP. So at LEP what you have is the interference between photon mediator and the Z mediator. and this can be factorized simply. The cross section E plus E minus going to FF bar goes as 1 plus A1, okay, times something essentially, okay, and this A1 goes to 0 means you get the photon cross, the QED cross section. A1 is the one which tells you the contribution coming from the Z essentially. So we have seen this, and the second observable we have looked at is the differential cross section. Okay, this cross section you can simplify it in terms of partial widths essentially. Okay, you can look at Z pole, this formula becomes very simple. Okay, at Z pole this formula becomes very simple, and then we have written some master formula essentially for the at the Z pole, and individually you can measure the decay widths in terms of the Z width essentially. If you measure the Z width and also the decay widths, you can extract all the information perfectly in terms of partial widths C, B, tau, E. And from this you can also get gamma invisible with very high precision. And so the E plus E minus physics is extremely simple, and you can do it by hand. You don't need a computer or something. Okay, you can actually do it by hand. You don't have worries about pattern distribution functions and then convoluting them with pattern distribution functions and none of this. Okay, so it's very simple 2 to 2 process, and you can actually compute everything. Then the other one we looked at is differential distributions. So this also has two parts. One part essentially is 1 plus A1 times 1 plus A2. Okay, so these are the observables at left. Okay, and from the differential distributions, we can get Z pole. Thank you very much. No, it's not. No, it is the opposite one. This one is not the one. There is softer one. This is dustless, but this is not soft. At Z pole, you have forward, backward asymmetries and various asymmetries you can have. Similar physics is done also at slack, where we have also discussed lepton asymmetries. Okay, with polarized beams. Slack, the main advantage is the polarization. Okay, so similar physics. And also at neutrino experiments. CCFR, CD, CDHS. Yeah, thank you. These ones are soft, I think. This is correct. Okay, this forward backward asymmetries and similar physics at slack also has lepton asymmetries, AE, mu, et al., which also gives me lepton universalities. So you have how many observables at the z pole? Essentially you have delta rho, delta r, SLD observations essentially, and then you also have the width, partial widths. Okay, so then there is another thing which we not often very take into consideration, which is called atomic parity violation. So there are some transitions which are in atomic parity, okay, which was so S 3s1 to 3p1, I think, if I remember correctly, transitions in atomic parity, which are also parity violating. Okay, and now they can also be used to get information about science data. Okay, it's also an observable essentially. So if you use atomic parity violation, many people don't use the fits, but Langacker uses it. Okay, so you can look at PDG and Langacker's textbook essentially to look at atomic parity, impact of atomic parity violation essentially, and those calculations are super complicated. They run because you had to calculate atomic spectra at very high precision and look at the transition rates essentially, and look at weak corrections for it. So you only normally look at QED corrections, right? Essentially, lamp shift, relativistic corrections, and so on. So essentially, okay. But now you also look at electroweak corrections to it, and see the transition about it. Weak corrections means Z corrections and everything. Wherever there is a gamma, there could also be Z, and that would be very very suppressed essentially. But if you want to calculate it, it's super complicated, and you do it, and then get some information about the transition, because the transition lines are very well measured, so they can also give you, but always they are always influenced by the meaning numerical calculations, because these are atoms which are very large atomic numbers, so you have to worry about the numerical transitions and numerical calculations, how well you have computed it, etc. So many people will take it with a pinch of salt, some people will take it seriously, but atomic parity violation is a serious topic essentially. So all this bunch of observables together, not from just left, from SLD, from Newton experiments, and from beyond lifetime, so on. So all these things together are called electroweak precision test. Okay, so when you do the analysis, you choose some particular observe, because, and as I showed you from the formula, they're all interlinked. They're all interlinked. So what you choose as inputs and what you choose as outputs is a very crucial thing. So typically you choose 5 parameters as inputs and predict 20 parameters roughly of the order of 22 parameters. All these things, forward, backward asymmetries, lepton asymmetries, all these things, and they're all simple calculations. No, you don't not. I have shown you the formulas and everything essentially. So these are all listed in one table essentially. You can calculate them, listed in table, and match it with the experiment. Okay. These formulas are given to you. They are all computed in standard model. Now, if there is any new physics, what you do is you compute these things in new physics and match. But standard model is measured, and but there are error bars. I will show you essentially. So the new physics should fit within the error bars. So that puts a very strong constraints on it. So, for example, I told you that I'll tell you. So this entire process is complicated, and typically one uses 2 computer programs which are called GFitter and also called another computing program Z fitter. Both of them have Ukrainian origins, and some bunch of them came off from here and they formed their own separate collaboration and everything. They take into consideration, they give you a global fit of electroweak precision measurements. So, given that all of them are interrelated, what you would do is you choose, say, for example, things which are well measured: gamma z, mz, sin alpha em, gf, and maybe one more parameter. I don't know, sin squared theta w also. Okay. And then these things you take them as inputs to your code. Sometimes you the MW measurement is also good, okay, and then predict, say, in SM within the standard model all the observables like AL, AFB, all the observations, okay, muon lifetime, okay, MW mass, M Higgs, so on, so everything you measure. So this entire thing is called electroweak precision measurement. I'll come to what happens in BSM, but let's first do it in SM essentially, so that we know what are the error bars. Input is renormalized input, the experimental input. So the point is, after renormalization, all these parameters are intermixed. Okay, totally other. So you can choose 5 of them to be your input parameters and then do a chi-square fit for these things. So that's the easiest way to do. That's the simplest way. So the paper, I would say, for you to do, if you want to do anything with electroweak precision test, I think modern, after the Higgs discovery, just follow this paper of Wells and Zhang. I think it will be there in the internet. I'll show you this thing, Wells and Zhang. So this is pretty good, and you can do it yourself. You don't have to in any model, not just standard model. So you know what are the measurements in standard model. Now you can go beyond standard model, redo this analysis also, because then he tells you how to do it. I'll come to that in a second. Essentially, okay, I'll just show you. I'll show you this paper also. So, but let's first stick to standard model and what are the inputs and the fits for it essentially. Now, so now these are the electroweak fits, okay, by choosing some 5 parameters essentially. Say for example 5 parameters. Now you see this is a fit within the standard model. We are not moving anywhere about the standard model. So within the standard model, you have predictions for mz, which is 91.18 something plus. So it is sitting there. That means it's actually taken as an input. It has 0 deviation essentially. Whereas gamma z has a small deviation, and sigma phi hadronic is also has a very large deviation. Like I said, it always spoils everything essentially. Then all these RLs are essentially I showed you, the ratios of sigma hadronic by sigma mu plus 1. Okay, RLs, forward backward asymmetries, with polarization, RB, RC, these are all again R's, you know that the hadron versus leptons ratio, which we had done yesterday essentially. Forward backward asymmetries, these are your lepton asymmetries. These are the lepton asymmetries with polarized beams in SLD. Okay, this is sin square theta W leptonic only. You cannot see it because it's written in green. So only leptonic part, that means you are not taking hadronic contribution. MW, sigma W, MT. Now MT is a very, very important part. So typically you either take it as an input or you predict it essentially. Okay, so if you take it as an input, you are better off essentially because there are bars and everything essentially. Okay, so with this now you can predict even before the Higgs was discovered what is the Higgs mass. So this plot is delta chi square. You do a chi square fit all these things, and Higgs mass is the only one which is not fixed. Everything is fixed. Now you see when the delta chi square goes to 0, it goes to 0 about 83, 84. So the electroweak precision test for all the observables, taking a global electroweak fit for all global observables, is essentially predicts a very light Higgs about 83 GeV. Okay. Now this yellow band is the band which was the Higgs is ruled out by left direct measurement. So the left direct measurement goes through a process called Z-Strelong. So what is that process? It just radiates a Higgs. The Z couples to the Higgs, so it just radiates a Higgs. So this process, so sometimes they write it as Z star and then Z and all. Okay, so it just radiates a Higgs, and you see that the Higgs can go into BB bar, photo bar. So you can take it a BB bar, and with this process you can put a limit on the Higgs mass. So you look at the cross section. So the maximum the left went to is around 210 in root S. Okay, so 210 GeV, and that could put a kinematic limit because this process was never observed. So that puts a process limit on M Higgs should be greater than or equal to 114.2. So you can just kinematically rule out this process. It's called Z-Strelong. And so this gives you a limit on this one. This small band is from Tevatron. They said they couldn't find Higgs in this particular region essentially. So with this you can predict what is the Higgs mass, and I'll show you you can also draw in top and Higgs plane. You will see other plots also. Now this is coming from LEP electroweak working group, which is a combination of experimentalist and theorist. Okay, it's a working group which is formed with experimentalist and theorist together, and so they form this thing and they put in the inputs, the theory inputs, everything, the standard model predictions and the deviations from the standard model. All these bars are called pull diagrams. Okay, so here 1 means it is 1 sigma deviation, 2 means 2 sigma deviation, 3 means 3 sigma deviation. So for example, this means that it is 1.5 sigma deviation. This is almost 3 sigma deviation from the standard model. No, 5 parameters are used as inputs for this, and then you predict everything, and then you get the theory prediction minus the experimental observation. Oh, that's a bar, and do a chi-square. So chi-square is defined as so you have some 10 observables. Say for example, there are 15 observables. Okay, so chi-square is defined observable theory minus observable experiment by sigma. Okay, now you can put a square and everything essentially on the top of it, and then delta chi-square minus chi-square mean. Okay, so this essentially is just fits the data. This is the theory prediction you know from the standard model and separate it from the experimental observation. For each observation you can have the formula, like I showed you the formula. These are all pre-level formulas. They are good enough actually. In some cases you need one loop for. Okay. Now the same analysis, instead of left working group, you can also use by Z-fitter. This is an independent collaboration. They also have very similar results like they have. So they also show that it is 80.33, but it could be slightly 80.22 or something. But it's yes, because it depends upon. So suppose if I want to, these are scheme dependent quantities. Okay, some observables if I use MS bar, some observables I use on shell. So each and what my inputs are, I may choose different inputs. Okay, each collaboration can use different inputs and everything, and in which scheme you have to do essentially. Okay.
All of the observables are like known, but the mass of the Higgs are not known at that time.
No.
From that we have the lower bound on the masses from the kinematic.
Right.
So, but after Higgs,
after Higgs, yeah. I'll just show you what happens after Higgs discovery.
Does it like rule out the other measurements or intention with the other measurements? Because the other measurements predict the Higgs value to be somewhat around.
No.
Light Higgs, they are predicting it from the. So you're saying
no, the Higgs is still light. Okay, so the upper bound on from this thing, this is the kinematic limit. Just purely from if you take electroweak precision test, the limit of the Higgs is from 80 GeV to 235 GeV. Because Higgs only goes logarithmically in the formula. So anything is a good fit. Okay, this is also not a very strong limit, but anyway, this is so it goes with. Now this is the latest thing. Now you input Higgs as well as an observable. Okay, so the Higgs is input. This is from G-fitter. Now the black bands are without the Higgs measurement, and the yellow bands are with the Higgs measurement. So with the yellow bands, you see they're doing perfect essentially, except some deviations and everything. The black bands are always sitting. Sin square theta leptonic, there are some minor connections, The moment Higgs is put in, everything almost sits with almost very close light deviation. There are these still small deviations between this leptonic and neutron observables. Okay, some people take the neutron observables, some people don't take the neutron observables. Some people take the atomic parity violation, others don't take atomic parity violation. So always read, these are slightly old also, but every year the PDG updates the electroweak precision test. Okay, so there's a nice review on it. So for the latest information, always look at the PDG. So most of the time Langaker is to write. Okay, so you can, it depends upon who does it, who writes it. Okay, okay, right. I don't think they use either of them. I think they take an expert from both the things. They give you PDG always takes a neutral stand. Always, it doesn't say which one is better. Okay. So all the colored ones are with when MH is taken into consideration, and you see the deviations are very little, and compared to when the MH is not taken into consideration. Okay. Now again with the prediction for the MH after the Z fitter, so MH measurements are sitting here, MW and the SLD measurements and LEP measurements. So LEP sits very nicely except for this SLD measurements which are slightly away, and the bottom part one forward backwards. Now one of the biggest quantity which is not very well measured is the MW mass. Recently LHC has updated its result, so the error bar on MW is very large. Okay, MW mass is very large, about 45 MeV or something such. The entire goal of LHC is to reduce the error bar on MW to 12 MeV, and recently they have achieved it. There was some noise by CDFs claiming that they have also achieved even higher precision of 9 MeV, and they made a measurement, but nobody believes that CDF measurement, and that's called the CDF anomaly, and it has a higher mass, 80.43 or something essentially. So that will rule out such a CDF measurement. If you take it, it will be not self-consistent with LEP measurements, and that requires all kinds of new physics, which is not easy to fit in. The standard model cannot fit in the CDF measurement consistent with LEP and other measurements. Okay, so but CDF hopefully will take away that measurement at some point essentially. Do you know that the CDF is a closed experiment, but the collaboration is still alive? So they have data which is very old, and CDF closed, the Tevatron closed around 2010 or something essentially. So, soon after the Higgs, 13, 14 I think they closed it down. But those guys are still active, and they are using the old data and claiming that they have a better measurement by doing reanalysis of the CDF data using new data analysis techniques. Okay. Anyway, so now without going into a CDF thing, what is the measurement? And you see here there is a region of between 0.4 and 0.37 essentially. This is the prediction of the electroweak precision test of the MW mass essentially at 1 sigma level. So there is a slight tension because the experimental fit is somewhere, so the best fit is somewhere here, and the best fit for the top, which is the other measurement which has the largest error. Top and MW has reduced, top also has reduced, it's the measurement has reduced. So both of them here, the prediction from the theory, these are, if you consider them as outputs of the electroweak precision test, this is how the graph looks like essentially. Okay. This is how the chi-square looks like essentially, and so you can do all this analysis, self-consistency checks of the standard model. Okay, So you measure something somewhere else and put them as input parameters and over constrain the standard model. Actually, the final answer is the standard model is super over constrained, and any slight deviation will lead to problem somewhere else. Okay. Now, this Higgs also contributes in the electron G minus 2, the muon G minus 2. So using the electroweak precision test and the G minus 2, because alpha input measurement was G minus 2 of the electron for a long time, then it became quantum Hall effect. So do you all know what is called as core data? These are the inputs. They tell you what are the explicit numbers. They are like standard. So SI measurements we have what is a meter, what is a length. Similarly, you have core data which tells you what is exactly the electron mass, what is exactly the lifetime of the muon, what is exactly this thing, what measurement should be taken. It's a collaboration again, and this information is put by the taken by the experimental collaborations. Okay, when they are doing these fits and everything essentially. Okay, if you use core data for muon mass and everything, essentially core data, and calculate electroweak precision test, there is a conflict with electroweak precision test and the Higgs mass prediction and the G minus 2. Okay, if you want to solve the G minus 2 by modifying the electroweak precision test, by playing with delta alpha hadronic and everything, then there is a conflict with the Higgs mass measurement. These are experimental, but experiments also, there are several experiments. So which experiments should be taken, which experiment should be, like I said, you don't want to, core data will not take CDF measurement because it's anomalous. So which experiment should be taken, which experiment should not be taken, and which should be the standard value one should use, because if some experiment analysis is dubious or systematics are large, it doesn't make any sense to use those numbers essentially. Okay, so they are very careful about what to do. So if you go to their website, they'll tell you all the numbers which you have to use, and that is used by Bureau of Standards and everything, and that is also used by various experimental collaborations and everything. Okay. This is the chi-square fit. So chi-square fits are ellipses essentially, because you know that is x square minus y square type diagrams. Now you just plot it in mw square and mh plane. Okay, it gives an ellipse, and this region is the one which fits for the data essentially, prefers the data. So you see there is a large region essentially at 1 sigma, 2 sigma contours and so on. The black point is essentially is the measurement. That's it. Okay. Now I'll come to S and T in 1 second essentially. Okay, let me stop this and then I introduce S and T. Okay, I'll just, these all I have not operated with LHC. LHC, the only main measurement which comes is essentially MW. Okay, so okay, I should have told about the CDF anomaly. I just tell you. So when there was a CDF anomaly, there has been a lot of papers which did the electroweak precision test with the new CDF anomaly. So there are many papers on it. Okay, but I didn't take it seriously, so I didn't bring it up essentially today. Otherwise, I should have shown you. But yes. So we'll bring it down again. So now that you know what are this electroequation test, and I try to convince you that I'll try to convince you that they will not only over constrain standard model, but they will start over constraining any physics beyond standard model. Any physics beyond standard model, they plot a very, very important constraint as long as it doesn't satisfy custodial symmetry. One of the first simplest examples we'll consider is so the two Higgs doublet model is so in the standard model there is only one Higgs, so phi 1, so which is called phi 0. Now instead of that you add one more Higgs, which is also a doublet under SU2. Okay, remember the standard model SU2 U1Y. See, the precision measurements have nothing, you okay, are more concerned with the weak sector. They are not more concerned about the QCD sector. So we can forget QCD. QCD is there. They'll play a role in terms of just adding NLO corrections to it, meaning next leading order corrections to it. Say for example, I told you about the mixed corrections, right? For example, so if there is a weak process, there could be QCD corrections to that weak process. So only there they can change the observable, meaning by magnitude of the observable. But the basic structure of the theory they won't change. QCD is unbroken theory, so it's not. So what we are testing most of the time is the weak sector. That is a complicated one because it has a broken generators and all this kind of situations. So I think I remember I gave you the example of BS gamma, right? So BS gamma, I'll just repeat for people who don't remember. So B2S gamma, so has UCT W. Now at one loop level it has a very different result. Okay, now if you add NLO corrections, which are gluonic corrections, okay, all these gluonic corrections, the result becomes super complicated, I mean accurate, because here the theory is still lagging behind the experiment. Okay, the prediction is super accurate in the experiment case, is around 2 to 5 10 power minus 4. This is the experiment. Okay, and the theory recently only 4 loop calculation has been done by Messiak essentially. All the 4 loop QCD corrections, not weak corrections. Okay. QCD corrections are already, because QCD is the dominant corrections on the top. So the process is a weak process, but on the top of it you have QCD corrections. Okay, you get the point, right? Essentially the process itself is a weak process because it's a flavor changing neutral current at one loop. So it has a charge current on the top, and so flavor changing current. So it's a weak process, but it has one loop loop corrections coming from gluons essentially. So the theory is just now reaching there essentially, but it still has an error bar larger than the experimental number. So the error bar of theory is larger than the experimental error bar. Okay, so if you have any physics in the theory, the form factors. So B sitting inside a B meson, essentially form factors, FB form factor. Those are about 20% error bars. So, but if you want to minimize it, you have to compute everything in most accurately by using some factorization theorems and so on. So and lattice calculations. So using the lattice plus the experimental thresholds and everything as input, we are trying to people are trying to reach as close as possible to the experimental number. How far they can go. Okay, and analog corrections coming from QCD essentially. Okay, so similarly, what was the point? Why I digressed? Okay, yeah. So we are looking at testing weak process most of the time. So now the first physics beyond standard model which you are looking at is just simply this. Now assume that both the Higgs get a wave. Okay, both the Higgs gets a wave. So that means phi 1 in vacuum phi 2 in vacuum So these are your Goldstone bosons. Okay, there are various Goldstone bosons. So like if you want, I can put them as G1, G2, and so the Goldstone bosons are complicated because they need not be coming from one Higgs. Okay, they need not be coming. So together there are only two waves and 1, 2, 3, 4, 5, 6 degrees of freedom extra essentially, plus the Higgs itself, H2. Okay, so the physical spectrum is complicated. The physical spectrum is 8 degrees of freedom to start with, and then 3 Goldstone boson. Why there are 3 Goldstone bosons? Yeah, why only 3? Because in standard model also there are only 3, because you only have 3 broken generators. Okay, tau 1, tau 2, tau 3 of the SU2. SU2 has only 3 broken generators. Okay, and so that gives you how many remaining 5 physical Higgses. So one Higgs with one Higgs doublet suddenly becomes 5 Higgses with just adding one extra scalar doublet. The assumption here is that V1 and V2 is equal. The second assumption is that it is charged under SU2. This is also charged under. You can also make the assumption that SU2, this is not charged under SU2. Those are called inert Higgs doublet models used for dark matter models. Okay, so if you don't charge it, okay, under SU2, they become something called inert Higgs doublet model. This is optional. I'll come to that in a little later. In that case, this Higgs need not get a wave. So it doesn't have it can be a doublet, it can be a singlet, whatever it is. It doesn't have SU2 charges, it doesn't have U1 charge, so it is just staying there. It may have U1 charge. So 5 Higgses are, if you do the calculation, minimize the potential and everything, there is a light Higgs, heavy Higgs, a pseudoscalar Higgs, and a charged Higgs. So this comes from the imaginary part of the potential. These two come from the neutral CP even part, essentially real part of the potential, and this comes from the charged Higgs part. Essentially, charge means essentially this part 5 plus part. The Higgs, two Higgses. Why two Higgses? Okay. Why a minimal Higgs? There are 3 generations. Why there should be only one Higgs part, essentially? Okay. There are, because there are, yeah. Okay. So these are CP even, or also neutral. It's called CP even in the sense they come from the real part. Okay. This is called odd, CP odd. This is also neutral. So this is parity violating, essentially. Okay. Okay. This is like a pion, say, if you want, essentially. CP odd means pseudoscalar. So these are scalars. This is a pseudoscalar and a charged Higgs. Now there is something called Weltman screening. I mentioned it, I didn't use the word Weltman, but when I was discussing this homework, it come in your assignment. What is Weltman screening? Weltman screening essentially tells you that any new particle or the Higgs should be such that it always protects the rho is equal to 1 relation. Okay, the rho is equal to 1 relation should always be protected all orders, or in other words, it tells you that Weltman screening is essentially another word for custodial symmetry. Okay, okay. So now the point is, if you write the potential, the potential Now, how does one get this potential? Uh, how does one get this potential? Is it God given or something? No. So because you know the gauge symmetry, you write down all possible terms which are invariant and with symmetry. Okay. So typically this is a, in fact, when I was a PhD student, one of the first year or first semester or something, this was one of the exercises I was given. The potential essentially of 2 Higgs and 3 Higgs doublet models. So this is very easy to do it because phi dagger phi is obviously symmetric. Phi 2 dagger phi mass terms are obviously symmetric. Then phi 1 dagger phi 2, the symmetry is conserved essentially. Then the fourth powers are obviously same. These are also same. This is phi 1 dagger phi 2 whole square plus phi 2 dagger phi 1 whole square essentially. This sum whole square. No, sorry, there is no sum. Yeah, right. Now there is a difference between this and this. This is the modulus here. There is no modulus here essentially. So if you take this combination, the star of this one and the star of this one make the Lagrangian real. Okay, this is A star B whole square and this is B star A whole square. So A star B plus B star A whole square, A star B whole square plus B star B whole square will remove the star ones. Okay, but that is not equivalent to phi 1 dagger phi 2 mod whole square. Okay, so these are all possible, okay, terms in the potential. Now how many free parameters are there? Lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. And how many Higgses are there? 5 Higgses. So you can interchange these 5 free parameters into the 5 Higgs masses because the mu square terms will go away in the definition of the waves. So in the definition of the waves, you also introduce some quantity called V2 by V1 is equal to tan beta. Pardon? They have the same. They are the same SU2s. There is only one SU2. These are the exactly same representations, but 2 of them. Now you can ask the question, how do you distinguish them? By their masses. Same. You can choose the opposite hypercharges, but for the present I wrote down the hypercharges and everything are same, except for the masses they are exactly the same. So they are like leptonic doublets, you are adding one by one, 3 generations. Same hypercharge except distinction in mass. So the same logic here also applies. Yeah. Right, 2 Higgs. There you choose opposite hypercharges. Okay. There you typically choose opposite hypercharges because you want to give differently masses to the. In supersymmetry is forced on us 2 Higgs doublet model because you don't have a way of conjugating things. So for example, scalar field you can conjugate by dagger, you can write down, and if you want to give masses to the up type quarks and the down type quarks, you need a conjugate. The same Higgs cannot work essentially. So in supersymmetry you cannot write the conjugate in the superpotential. It's an analytic function. It's either you write it in terms of completely z z z, or you write it in terms of z z star z star z star. It's an analytical function. So because it's an analytic function, so you need 2 Higgses, one to give to up type and another to give down type. Now this Lagrangian, it breaks custodial symmetry. Okay, since we are looking at the first, I'll come to the more interesting features of SU2. This is just introduction to the 2 Higgs doublet model. We'll go into the greater details later on at some point. So this breaks custodial symmetry. How do you see that it breaks custodial symmetry? Is there an SU2 times SU2R symmetry here essentially which breaks? So custodial symmetry, the best way to look at is so the lambdas should meaning, so if you take phi 1, phi 2, phi 3, phi 4, they have an SU4 symmetry. The SU4 symmetry can be written in terms of left symmetry, left read 2 SU2s essentially. You can write it in terms of 2 SU2s. So that is your custodial symmetry. One SU2 connects to your plus minus charges of the W and the other with gamma Z essentially, the two essentially 2 SU2s. These 2 SU2s, okay, are broken by these 2 waves because there are 2 waves and there is always a misalignment if the waves do not align with each other. That means the waves should always be close to pi by 4, pi by 2, the angle. So these waves, they cannot take any value they want. Okay, so the reason is at the end of the day, the electroweak precision tests tell you that the angle, the electroweak symmetry breaking is almost like it is broken by a single Higgs. The moment you have a second Higgs and with its own wave, then it spoils the custodial symmetry. So the electroweak precision tests are already telling you that you cannot fit in a second Higgs unless they are aligned. So they are aligned essentially. They are aligned. Now you can explicitly calculate this relation. What is the electroweak precision the rho parameter? So this delta rho parameter, if we calculate explicitly in the 2 Higgs doublet model, it has the following formula. This delta rho is just a function. I'll just define what it is. Ma square there is a simpler formula in the alignment limit in our paper. You can look into it, but okay, I'll show you the formula. Now what is this function f delta rho of any two masses m1? Something is wrong. Oh, okay, fine. Yeah, right. Okay. There is a minus sign here. Okay. So this means now you know what is delta rho. Delta rho should be 10 power minus 4. Okay. So what it means is that either this logarithm should still be suppressed essentially. So close to 1 so that they all go to 0 or something essentially. And the mass difference and this mixing the angles, I'll tell you what these angles are. Okay. Beta is the ratio of the waves, tan beta essentially. I told you. Alpha. So how will you get the mass matrix of this potential? So you take the mass matrix of any potential is defined as okay. This is any potential, any fields. Now, so then you have one thing which is called scalar mass square matrix is nothing but delta of real phi 1 delta of derivative of real phi 2 v. Okay, the neutral components phi zeros essentially. Okay, real components. Okay, the second one would be pseudoscalar. So pseudoscalar, the neutral, this is neutral, is also neutral. The same potential in the vacuum essentially. Okay, this sign means vacuum. Imaginary phi 1 similarly you put charge pi plus pi minus, you get the third matrix. It turns out only this one is a 2 by 2 matrix. All the others, this contains 2 Goldstone modes. The charge Higgs contains 1 Goldstone mode. Okay, so this contains 2 Goldstone modes. So that means 2 eigenvalues are 0 and only one non-zero eigenvalue. So which we call it as A pseudoscalar Higgs. This contains 2 by 2, no zero eigenvalue, both of them are real matrices, and the mixing angle between them is called alpha. And the charge Higgs m square charged is dot square phi 1 plus phi 2 minus at vacuum has 1 zero eigenvalue and one non-zero eigenvalue, which we call as H plus minus. So this is a Goldstone mode. These are also two Goldstone modes. So remaining are 1, 2, 3, 4 and 5. Okay. So 3 Goldstone modes, 8 degrees of freedom, 3 Goldstone modes, 5 physical parameters, and the mixing angle alpha is the one only for the neutral part. Okay. Now you look at this formula and tell me when this will be very close to 1. Because the experiment tells you that they should be 1. So this will be very close to 1 when these are very degenerate or these are very degenerate. So any two sets should be two degenerate. Either the heavy Higgs, heavy neutral Higgs and pseudoscalar, heavy charged Higgs, heavy neutral Higgs and heavy pseudoscalar Higgs should be degenerate, or the pseudoscalar should be degenerate with charged Higgs and everything, or this should be completely degenerate. If some of them are degenerate, this will end up being very close to 1 essentially. So typically you take the case mh square neutral degenerate and very heavy. So that mh square so the light Higgs is identified with the standard model. That won't be sufficient. You also need beta minus alpha close to pi by 2, which is called the alignment limit. So in the alignment limit, only in the alignment limit, the two Higgs doublet model works. This entire thing called alignment limit. There is also one other limit called decoupling limit. Okay, when you see these papers and everything, they will say alignment limit or decoupling limit. They'll make a lot of broha and everything. That's purely because of the rho parameter. Okay, it's purely because of the rho parameter. The other limit is called decoupling limit, in which all the extra Higgses other than the standard model Higgses are greater than TeV. So then all the loop calculations will be decoupled. I didn't come to the decoupling limit theorem. I'll come to that essentially. All the loop calculations will be highly suppressed if one of the masses is very, very large essentially. Okay. One of the masses goes to infinity, say for example, the loop contribution goes to 0 corresponding. But this, what it shows you is that one, the delta rho adding an additional Higgs breaks the custodial symmetry drastically, and the consequence is that it makes the rho parameter quadratically sensitive in the masses of the extra particles, these extra Higgses. So you hope that decoupling limit works, essentially that the loops are well behaved. Okay, it works in this two Higgs doublet model, but there are cases in which decoupling theorem is violated. That means that even if you take the masses to infinity, okay, I'll come to the second limit. I'll just mention what is the other one. So if you have a typical loop diagram, I'll come to the proper definition of decoupling theorem later on, but this I'll just mention the statement today called I'll do the statement and everything, but the point of this theorem is that in the limit masses in the loop are taken to infinity, the loop contribution should go to 0. Such theories are called decoupling theories. So such theories are called decoupling theories. So that means that the masses, so they, if you, it is easy to understand whether it's a loop diagram or anything. If the propagator has an infinite mass, okay, you can forget about the propagator and just put the mass and it becomes an operator. So if you have a loop in the, where the particle has an infinite mass, so it just becomes, it doesn't matter what it is, essentially it just becomes one, essentially the entire thing. So if it is logarithmic divergent or anything, if it is a decoupling theory, that means the loop just should collapse, if it is a meaning, if it is okay after renormalization. Now there are a lot of violations of it, especially with scalars, but this word decoupling is typically used interchangeably as the limit in which you take the masses to be large, very large. So the loop contributions corresponding to those particles are very, very small. And some theories are non-decoupling. Okay, some theories are non-decoupling and some theories are decoupling. So the theories which are non-decoupling will still be sensitive to the loop corrections will still be sensitive even if you take the limit which are sending to infinity, like Technicolor. It's a non-decoupling theory. Okay, so the other, so we'll come to Technicolor second, essentially. Okay, yeah, maybe what is the time now? Oh, maybe next class essentially. Okay, yeah. So the other limit is called the decoupling limit, in which the rho parameter goes to very close to 1, is the limit when all the other masses, Higgs, so this is called the decoupling limit. Now there are several variations. Now because there are two Higgs doublet models, meaning there are two Higgses, depending upon how you give it to masses to the fermions. So whether both the Higgs give masses to the fermions to the in the same way, that's called type 1. Okay, then there is type 3, there is type 2. So one of them gives you up type masses, another gives you down type masses. One of them gives masses to leptons only, one of them gives to quarks only. So that's called type X. So then there is the opposite direction which is called type Y. So there are variations of this two Higgs doublet model. In the recent times, why it became interesting is this garnered a lot of interest is because if one of the pseudoscalar is light, okay, if one of the pseudoscalar is light, it can explain the G minus 2 problem at 2 loop level. Okay, at the 2 loop level, so G minus 2, I'll come to it. I didn't want to come to it because of the lattice results which rule it out, but anyway, which say that there is no problem, okay, in the standard model, okay, calculation, but I'll just mention it briefly. You should know. If you have questions, I can elaborate on it, but we had a lot of talks on it anyway. So the muon G minus 2 has contributions from QED, electroweak, these are the two main things, and the QED part, which is also called hadronic vacuum photon. QED part, so this electroweak part comes at 2 loop, 3 loop is small, it's not done. This is on the 2 loop. QED 5 loops estimate. This is the dominant part. Okay. So if you remove this is so 2 loop and headbanding, they have also error bars. These are the ones which have error bars. Hadronic vacuum polarization and H1. So one is this diagram with pions in the loop essentially. The other is light by light hadronic. So this is connected to the muon. Okay. If we have hadronic particles, essentially, that's the point. Okay. Now hadronic light by light and everything. Let's say these are under control, but they can be error. The error, the size of the error is of the size of electroweak correction from the standard model. So delta essentially G minus 2 of the muon is roughly of the order of electroweak. So when I say delta means delta G minus 2 muon is equal to delta G minus 2 experiment minus G minus 2 theory. So this estimate, the error bar which doesn't match with the thing, is roughly of the order of electroweak, which is of the order of 200 or something, into 10 power minus 11 units, okay, into 10 power minus 11. So this 200, that means if you have a new contribution in electroweak, this can be explained. So this was always thought of as a signature of new physics. Okay, because the error, which is why people got so excited that new G minus 2 is a signature of new physics, is the error bar is roughly of the size of the electroweak contribution. In the electroweak, the main contributions come. There are errors here, assuming that these are all under control. We had several talks on G minus 2, but if you want, we'll have one more. But anyway, so the main error bar, the main diagrams in the electroweak are something called a 2 loop, which are called the bar Z diagrams. So one gauge boson, one Higgs, okay, at 2 loop. So mixture of one scalar and one gauge boson. So these are called bar Z diagrams. One loop diagrams you can draw anyway. So these are called bar. There are a bunch of diagrams of this. These are called bar Z diagrams. So these are the ones which contributed to loop. Now, if you have a light pseudoscalar, instead of this one here, you'll also have a scalar pseudoscalar here, which will add an additional diagram, and that requires MA to be around, I don't know, less than or equal to 60 GeV, and tan beta also between 20 to 60. Then this can explain the G minus 2. That was the reason, by keeping in the alignment limit. So how do you choose the alignment limit? Now decoupling limit will not work here. You need the alignment limit. So you keep the alignment limit with the heavy neutral and charged Higgses. So you make them degenerate. Okay. Then you satisfy the alignment limit, and beta minus alpha is pi by 2, and then through these diagrams you can explain the G minus 2. Okay. So with this, that is the reason why this became very popular, and people started looking at why G minus 2, how you can probe G minus 2 explanations by this pseudoscalar Higgs essentially. So there was sort of a revival of this two Higgs doublet models because of that essentially. Anyway, after the Higgs discovery, there was a lot of interest in two Higgs doublet models, because people thought that there should be another Higgs at least. Why only single Higgs actually? Okay, yeah. Okay, so this is the story of our first BSM model, which is, I didn't do the details. The details will be left for assignment. Okay, and then you can work out the details. I'll give you the references also. Yeah, I still didn't come to my STU parameters, which I'll do next week, and then we will go to the next module. Okay. G minus 2 is there in the G minus 2 details are in my notes. Okay, I'll get it. One notes I already put it on the Teams. Another notes I'll put it up once this is scanned essentially by the weekend, and I'll also put up the assignment. Now I have some questions I can ask essentially because I covered some ground. Okay. Okay. Yeah. Any questions actually? Yeah. Supersymmetry also has two Higgs.